All right. Last time we spoke about transistor as a switch. We say there are two major uses of a transistor, which is a transistor as a switch and as an amplifier. Another use of a transistor is we use a transistor as a regulator. But for now, we are going to talk about transistor as an amplifier. There are three ways in which we can set up a transistor. We call that setup as transistor configuration. We have what you call common emitter configuration, common base configuration, and common collector configuration. Why do we call them common emitter, common base, common collector? In this case, you can see on the common emitter configuration, this is our emitter terminal. And our emitter terminal is common to both the input and the output. And on the common base, you can see that this is our base terminal. It is also common to input and output. And the collector terminal, you can see that the collector terminal is also common to both the input and the output. That's why we call them common emitter, common base, and common collector. There are characteristics that you're supposed to know about the setup of the common emitter configuration. Right. The first one is there is 180 degrees phase shift between the input and the output signal. You can see that we have a positive input here. That positive input results in the negative output. So we are saying there is a 180 degrees phase shift between the input and the output. When we have a negative input, we have the positive output. So there is a phase shift. Then we also have the average values of the input and output impedance. Remember, impedance is the same as resistance. A transistor is known as a transfer resistor. So we're saying the average values of the input and the output impedance. Then, with another characteristic for common emitter configuration is it has high current gain. Remember, last time we talked about gain. That gain is equal to output divided by input. So we are saying there is high current gain when we say collector current divided by base current. Then there is also high voltage gain. That is another characteristic of a common emitter configuration. Then the common base configuration, the characteristics for common base configuration, there are no phase shift. In other words, when you have a positive input, you have a positive output. A negative input results in a negative output. So there is no phase shift between the output and the input. Then another characteristic is the current gain is less than 1. In other words, when we say collector current divided by base current, we will get a result which is less than 1, which is more of a decimal number. So we're saying the current gain is less than 1. Then it also has a high voltage gain and it has low input impedance. Impedance, remember, is just the same as resistance. Then it has high output impedance. So these are characteristics of a common base configuration. Then the common collector configuration, in this case, doesn't have a phase shift. There is no phase shift between the input and the output. Then there is also high current gain. You can see that common base is low current gain. Common collector is high current gain. Common collector is the voltage gain which is less than 1. Common base is current gain which is less than 1. Then common collector, it has high input impedance. Common collector has low input impedance. Common base. Then common collector is low output impedance. So you must know these characteristics of these configurations. All right. Then now we want to talk about biasing. Biasing of our transistor. We do have a circuit diagram like this, whereby VCC is our voltage, is our biasing voltage. So the biasing voltage, we are going to take it as 10 volts in this case. All right. So remember the characteristic curve that you spoke about last time. Characteristic curve consists of VCE, which is the voltage between the collector and the emitter. Are we together? Which is this VCE. Then on this axis, we have the collector current, which is IC. All right. So we do have this equation that says VCC is equal to VRC, the voltage drop across our load. This is our load. Voltage drop across our load plus VCE. So we're saying VCE plus the voltage drop across our RC is equal to VCC. So let's say we have a situation whereby our transistor is in the cutoff region. Remember, in the cutoff region, there's no current that flows, so there won't be IC. So in this case, when we don't have IC flowing, so it means the VRC will be equal to 0. So if VCC is 10 volts, if VCE is 10 volts and VRC is 0, that means VCE will be 10 volts. So we'll be having this point, let's mark this point as our 10 volts on our VCE. All right, then we said in the saturation region, we said the moment we start increasing base current from IB0 to IB max. Remember, when you keep on increasing the base current, we reach a point whereby an increase in base current won't have an effect on the collector current. And we said at that point, our transistor will be in the saturation region. In the saturation region, remember we said our transistor will be fully on. So when our transistor will be fully on, that means maximum current will be flowing through our load resistor, which is RC. In this case, the voltage drop across RC, VRC will be approximately equal to 10 volts, which is the supply voltage, which is the biasing voltage. So in this case, we are saying our IC max will be flowing through our load. So in this case, in the saturation region, our IC will be maximum in the saturation region. Are we together? So now we do have 2 points, which is one along VCE and another one along IC. If we connect these 2 points, we form this other line, a straight line that we call a load line. This line is called a load line. Are we together? So remember, we're talking about transistor as an amplifier. So our transistor, in this case, it acts as an amplifier in the active region. Remember, this part represents the active region. This part represents the cutoff region. This part represents the saturation region. All right. So our load line represents the characteristics of an amplifier of our transistor. So along the load line, there is a point whereby our DC characteristics will be present, and AC characteristics will be absent. And those point at that point we call it a Q point, which means quiescent or quiet point, something like that. Are we together? At Q points, only DC conditions exist. Are we together? But this is the point whereby we input our AC signals. All right. So in this case, we want to see classes of amplification. We have 3 classes, which are class A, class AB, and class C. All right. Let's look at this. Now we have a characteristic curve that is a Q point. Now we have a characteristic curve that is a Q point. All right. At class A, and when we have an input signal that is at the center of the load line, we form. Okay, let's look at this input signal. Sorry. All right. So here is our input signal. Our Q point is at the center of the load line. Remember, this is the input signal. Then output signals are along IC. All right. Our output signals, it's going to be like this. So our output signal will be like that. Are we together? So this is a class A amplification. Our input is at the center of the load line. All right. Now let's look at class AB. Class AB amplification. Class AB amplification, input signal is at the cutoff region. This is the cutoff region. Let's draw our load line. Then, yeah, at the cutoff region, that's where our input signal. So, we're going to have this, then our input signal is always in AC. Are we together? Now we have to see our output signal, how our output is going to come about. All right, it's going to be like that. Okay, so our output is going to be just, should be something like that. All right. Oh. Our output is going to be like that. Are we together? We're not going to have a full AC output. Why? Because, remember, this is the cutoff region. So, the other part of our input is going to be cut off because of the cutoff region. All right. Then we have a class C amplification. Class C amplification, the input signal will be below the cutoff region. So here is the characteristic curve with a load line. So we're saying, oh, somewhere here. This is our input, our Q point along the load line. Then we are going to have input signal something like this. All right, something like that. Then the output will be just that. How we together? So these are three classes of amplification of our transistor. In this case, we are explaining the operation of a transistor as an amplifier. I think that's all.